Okay, now we're going to let something accelerate. Okay, now it's going to get exciting. In the 65th minute, it's going to get exciting. It's like a soccer game. Right? Let's see. Except it's going to get exciting. An international soccer game, not the women's soccer here. Those are all exciting. It's the international games where nothing happens. That's what I meant. Okay. So now we're going to do a demo and think about something called shoot and drop. Shoot and drop. And the question in shoot and drop is who hits first? Okay? So this is shoot and drop. You may have seen this before. This is a very popular, common demo that everybody does, right? There's these little thingy-bobs here, and one of them is going to get shot that way. And one of them is on a little rod. It's just going to get dropped. And the question is, which one will hit the ground first? Right? Which one will hit first? Will the motion this way change what happens? Let's think real quick. All right, so here, what am I plotting? I'm plotting y, and this is a trajectory, so I'm plotting x like that. Okay? So this is drop. It's not going to get shot to the side. It's going to start here. And we know from last time it's going to accelerate down at 9.8 meters per second squared from last week. And then shoot will look something like this. All right, here it is. And it's going to be given an initial velocity, v naught. Okay? So in the x direction, it's just going to move forward with that velocity. But in the y direction, it's also going to accelerate down. Because we know it's going down, everything falls at 9.8 meters per second squared. And this is another case where the two motions are not coupled, where they're independent. You treat them independently. So I'll give you a hint. What's going to happen is this one's going to drop. And this one makes a motion like this. Okay? It looks just like the kinematics graph, doesn't it? Like a parabola. But it's actually a trajectory. And the reason it looks the same is the x-axis here and the x in time are both linear. Never mind. Don't worry about that comment. Okay, let's watch it drop. Let's see. How long does it take to get down? Y final equals y initial plus vyt minus 1/2 gt squared. So I put a minus because it's dropping, because g is just a positive, is a constant. Constants aren't negative. So it's negative 9.8 meters per second squared. Okay? So I could put in some numbers and say we want it to get down to 0 and start at h, right? So the final is 0. The initial is h. It's not moving. We drop it from rest, minus 1/2 gt squared. So you could solve that for when does it hit? It hits at the square root of 2h over g. Right, the square root of 2h over g. T square root of 2h over g. Fine. This one's moving in 2D. We've got to solve both. Okay? So for the y, we say y. We say this basically the same thing. It's y final equals y initial plus vyt minus 1/2 gt squared. All right? Okay, so in the y final is 0. The y initial, it started at h. Is it moving in the y? No, we're shooting it this way. So v naught vector is vx I hat plus 0 j hat. Right? It's level. It has no y component. Therefore, this term is 0. See that? Minus 1/2 gt squared. So we solve that for t. What do we get? Square root of 2h over g. Did we even use the x component? No. Right? Because they're separate. So how long it takes to fall is completely independent of how fast it's going this way. We could do the x motion. We could say x final equals x initial plus vxt plus 1/2 at squared. Okay, is it accelerating in x? No. That's 0. Where did it start? It started at 0. I'm sorry, the final position of x is x final. X initial is 0, vxt. So we see in x, it's just d equals vt. Right? So when it drops, it falls just like this one falls, and it just cruises that way. And when you put those together, it makes a parabola. That's all it does. Okay? So let's see if that's true. Let me check these questions real quick. Shouldn't the graphs reflect? Oh, no, that's old. Why is R not a vector, not a scalar, if the position is at the beginning? I understand. Yeah, I'm not sure. And let me just check the last one. Yeah, there's some concern about the initial, that old R naught. We'll get to it some other time. Okay, so here it is. So we're going to see this one's just going to fall, this one's going to shoot. And the only way to test this is by listening. You want to listen for them to hit and see if they hit at the same time. Let's see. I think they hit at the same time. Did anybody hear 2 hits? I only heard 1 hit. Let's do it again, just because it's fun. Okay. And that one's going to get shot, and that one's going to get dropped, and it has to be level. If it's not level, what do we make non-zero? By, exactly. Ooh, let's do it non-level. Let's see if they hit at the same time. This is like the counter proof. Oh, they didn't hit at the same time, did they? I've never done that before. That was exciting for me. I enjoyed that. Quick questions, and I'll tell you what people get wrong about this. Why is it negative? Yes, so this is important, okay? Why is it negative 1/2 gt squared? So in the general formula, it's plus 1/2 at squared. But we want to say we know the real, I made y up positive, and we know the magnitude of the gravitational acceleration down is 9.8, and we know it's down. So I manually plugged in minus 9.8 for A. Okay? So I put the minus here, and I put the 9.8 here. Okay? You could, if in your brain, if you're good at this, you could say, no, I'm going to put a positive there because I'm going to remember that G is negative. You could. It's not a good idea to define constants negative, but you could. And then you get to here and you'd say, oh, no, I have a negative sign here. You can't have a square root of a negative. You'd say, oh, no, don't worry about it because I know the value of G is negative. And you're just going to confuse yourself. Okay? So don't ever define a constant negative. The constant is 9.8. The negative is because you know it's going down. Okay? So whenever you do this demo, people say, oh, but wait a minute. What if it was going really fast? Right? If it was going really fast, they would have hit at different times, right? Like, no, they would still hit at the same time. It doesn't matter. It's uncoupled. They say, okay. But what if it's going really fast? Like, what if it's a bullet? I'm like, no, it would hit at the same time. That's like the whole friggin' point of the lecture is it would hit at the same time. They're like, no, but we're not so sure. So we're going to do a bullet, right? So this is what we're going to do. And they're going to hit at the same time approximately here. So let's see. I'm going to drop one and shoot one, and we're going to see if they hit at the same time. And you're just going to say they are because you can't follow it this fast, and your head doesn't turn fast enough. Here we go. 1, 2, 3. Roughly the same time. I didn't quite have, I had the angle a little wrong. Let's see. Roughly the same time, okay? It doesn't matter. And then they say, what if it's going really fast? What if it's going really... Okay. Oh, wait, I need one. Ow. Okay. So it's going really fast. Wait a minute. And then we get level close to the same time. But wait, what was that noise? Dr. Stenson messed up. Everybody listen. Did that follow a normal trajectory? No. Because eventually your model breaks down. This is what we can learn from this, is your model is eventually going to die. What is our model? Our model is that everything just falls at 9.8 meters per second, and when it goes this way, it has no force. But if something's moving fast through the air, it has a force, right? It has a drag force slowing it down. And based on the shape of how it goes through the air, it can have lift, picking it up. So the person I scream at is actually correct. Eventually, they won't hit at the same time because other things outside your model will start to take over. There's even another one. What if we sucked all the air out of the room? What if we're on Mars? Okay? Now let's say we're on the moon, and we do this experiment. And here we are on the moon with some gravity. It's less gravity. The thing will go like this. And you shoot it harder, it'll go like this. You shoot it harder, it'll go like this. You shoot it harder, it'll go like this. Will the model ever break down? Yes. Because the moon is curved, so is the Earth. Right? Eventually, you would go into orbit. Right? So every model will break down eventually. But for all the problems you're going to do, they're independent. Okay?